All right, so based on all of the things that we have talked about for over 40 slides or so, we can understand now that plate tectonics is a super important process that currently shows us how the continents are positioned and how they were positioned in previous times. So, for example, we know through plate tectonics that it was about 180 million years ago that we started the breakup of Pangaea. Pangaea was a supercontinent, as it was called, not the first supercontinent that the world has had. There was a previous one called Rodinia, but the most recent one for sure. So the supercontinent, which I think most of you are familiar with, again, Pangaea was the name of it, and it looked something like what you're seeing here on the bottom image of the slide. When all of the masses were placed together, it looks similar to this. So this is already starting to break up. Originally, they were even further closer together. And so when they were close together, there was a massive sea surrounding it that was called Panthalassa. And there was a smaller inner sea in between these two sub-land masses called the Tethys Sea. So this massive supercontinent of Pangaea formed thanks to plate tectonic movements as well, and split apart also thanks to plate tectonics. So you see how initially North America and Eurasia split from the southern hemisphere. That's the first thing that kind of started happening, creating two large land masses called Laurasia up north and Gondwana land in the south. Then each continent started separating, except for Europe and Asia, of course. And then India itself actually, which was a separate landmass, collided against Eurasia, which started happening about 50 million years ago. And we'll go through the steps of that soon. So what you're seeing here is a progression, step by step, of how the breakup of Pangaea happened. So initially, the two subcontinents of Laurasia and Gondwana started to separate, and that was about 180 million years ago. Laurasia was made up from North America, Europe, and Asia, minus India, I should clarify that, and Gondwana land was made up of South America, Africa, India, Australia, and Antarctica. By this time, India had already started splitting from the rest of Gondwana land, as you can tell here. But as you can see, that looks a lot like what Alfred Wegener had envisioned when he came up with the continental drift hypothesis itself as well, which is pretty great. In the next image, which was, or the next depiction, which is 135 million years ago, where you see that North America started to split up from Eurasia as well. And you also see that South America started slowly to spread apart from Africa. You also see that India is further north, making a fast trajectory towards Eurasia. And you see that South America and Africa are both further north from Antarctica and Australia at the time. The next image, which is 65 million years ago, is when we see a lot of spreading that has actually already taken place. So you see that South America and Africa are really far apart now, and that there is further spreading from North America, from both Africa and from Eurasia as well. And you see that India is further north, almost all the way to Eurasia, and yeah, much further from Antarctica, as well as Africa, much further from Antarctica. And then finally, the present age shows the final fast spread of North America from Eurasia, and from Australia, that was incredibly fast spreading also from Antarctica. India's movement throughout has been said also to have been one of the fastest movements of plates, by the way. So the trajectory of it the trajectory that it took went close to 70 degrees in latitude in a pretty short time frame. So within 130 million years, it moved 30 degrees in latitude. Again, based on all the current geologic knowledge that we have, The plate tectonics theory actually solves a bunch of mysteries, one of them being the fossil data discrepancy that Alfred Wegener had found in the southern hemisphere land masses, for example, as it's shown in the image. It solves how some of those fossils could have been found on many continents, even though the organisms were not marine travelers or had the means of ocean travel for that matter, by stating that the land masses must have once been together. The theory also explained the striations, or those lines again that were left by the retreating glaciers after the glaciated period that happened 300 million years ago, and that they seemed to be apparently random beforehand, before we found out that they were together in random directions, but once we placed them together, those retreating lines made a lot more sense. So, we've thoroughly talked about plate tectonics and how it works, and we've said that the main force that is responsible for plate movement is convection, or that is the hypothesis right now. But there are two mechanisms that allow for the movement to happen. So within convection, there are two kind of sub-forces. The first one is called ridge push, which is when you have a spreading center, and then the second one is called slab pull, which is when you have a subducting plate at a continental oceanic or a oceanic convergent plate boundary, basically. So this is ridge push, this is slab pull. So it is understood now that slab pull is by far more influential than ridge push, and it is both more common and stronger at driving the subsequent processes needed for plate motion. All right, so with that, we are done with covering the internal structure of the Earth and the theory of plate tectonics, which was initially aided again by the continental drift hypothesis, and it really was helped by the exploration and mapping of the seafloor. That was one of the main reasons why it came about. Aiding tools that came along the way in discovering the theory of plate tectonics were radiometric dating, ocean floor drilling, and bathymetry, which is basically mapping of the ocean floor. So those are main tools that came about. So now what we want to do is go ahead and think about how plate tectonics is truly responsible for some of the natural processes, which sometimes become hazards, disasters, or catastrophes, which we have ongoing today. So I've already talked about some of those natural processes for which plate tectonics is responsible, such as earthquakes and volcanoes, but I want you to think about how these two different processes, earthquakes and volcanoes, can be linked to secondary natural processes, which can be hazards depending on location and on situation. So think about environmental unity here. All right, so that is all that I have for you here on Chapter 2. As always, let me know if you have any questions. I am happy to help you in whichever way I can.